Huawei did not build a 1-nanometer chip. That headline is wrong, and the real story is bigger than that fake claim. In May 2026, Huawei's chip chief He Tingbo unveiled a new design called logic folding at a conference in Shanghai. It skips 1-nanometer lithography completely. It stacks transistors instead of shrinking them. That one decision might threaten TSMC more than any single chip ever could. To understand why this matters, go back to 2019. The United States hit Huawei with sanctions. Washington pressured the Netherlands to block a Dutch company called ASML from selling its most advanced machines to China. ASML is the only company on Earth that builds EUV lithography machines. EUV stands for extreme ultraviolet. These machines fire light at a wavelength of 13.5 nanometers to carve tiny circuits onto silicon. Without one, making chips smaller than 7 nanometers becomes nearly impossible. Each machine costs between $150 million and $380 million. Washington's plan was simple. Cut off the machine, and China's chip industry freezes in place. For a while, it looked like the plan worked. Then in September 2023, Huawei released the Mate 60 Pro phone. Engineers cracked it open and found a 7-nanometer chip called the Kirin 9000S inside. It was made by SMIC, China's largest chip maker, without a single ASML EUV machine. That crack kept growing. Reports from 2025 placed Huawei engineers at a facility in Dongguan, testing pieces of a homemade EUV machine. The light source came from research at the Harbin Institute of Technology, using a method called laser-induced discharge plasma, or LDEP, instead of blasting a laser at flying tin droplets the way ASML does. The LDP method vaporizes tin between two electrodes and zaps it with electricity. The result is the same 13.5 nanometer light that ASML machines produce, just made a completely different way. Trial production was set to start, with full manufacturing targeted for 2026. But here is the part almost nobody explains clearly. A working EUV light source is not the same as a finished chip machine. Commercial lithography needs at least 250 watts of steady power to run fast enough for factory use. Huawei's early prototype reportedly produced somewhere between 100 and 150 watts. ASML's newest machines push past 500 watts. So how is Huawei actually building chips right now, while that gap still exists? The answer came out in a report from the American Enterprise Institute in April 2026. Researchers found that SMIC has already proven it can make 7-nanometer chips reliably. It is also working on 5-nanometer chips, though yields sit at only about 20% right now, meaning most of what comes off the line does not work. The report explains that Huawei is not waiting on the homemade EUV machine at all. It is buying older deep ultraviolet machines, models like the ENT1000 1980 Sapphire, that current export rules do not even restrict. China reportedly bought around 90 of these machines in 2024 alone, worth billions of dollars, right before anyone thought to add rules against them. Using this older equipment and multiple patterning, Huawei is aiming to produce 1.6 million high-end logic dies in 2026 for its own AI chips. That number should stop you for a second. That is not a lab experiment. That is a supply chain built specifically to dodge the exact machine the West blocked. Now back to logic folding, the announcement that actually deserves the spotlight your title promised. On May 25, 2026, He Tingbo stood on stage at the International Symposium on Circuits and Systems in Shanghai and presented something called the Tau scaling law. The idea behind it is not to etch smaller circuits at all. Huawei claims this design reaches a transistor density equal to what a true 1.4 nanometer chip would deliver, but not until 2031. And not by actually printing at that resolution. It is density through stacking, not density through shrinking. Here is why that fall 2026 date is the real cliffhanger. If Huawei ships a working Kirin chip using logic folding on schedule, it proves China found a way to keep gaining computing power without ever needing an ASML machine again. That would not just be a workaround. Meanwhile, TSMC is not standing still. In the second half of 2025, it began mass-producing true 2-nanometer chips using gate-all-around transistors, with yields reportedly above 60%. Companies like Apple, Nvidia, and AMD already locked in production space for years ahead. Samsung tried to keep pace but is struggling, with 2-nanometer yields sitting around 40% and 3-nanometer yields around 50%, compared to TSMC's 90%. So the real headline is not that China built a 1 nanometer chip, because it did not. The real headline is that Huawei found two different ways around the exact wall the United States built in 2019. One path runs through a slow, imperfect homemade EUV machine still years from matching ASML. The other runs through legally purchased older machines and a stacking design that could ship real product before this year ends. Watch fall 2026. That is when the world finds out whether logic folding was a slide in a conference room or a chip inside a phone. And if it is the second one, TSMC will not just be on alert. It will be facing a rival that stopped playing by the old rules entirely. Something that should scare every tech company on Earth. Zero. That's how many of their most advanced AI chips are shipping into China this year. Not fewer. Not reduced. Zero. A $50 billion market walked out the door, and it didn't collapse. It built its own replacement instead. This is the story of how one banned company built a chip good enough to make Silicon Valley nervous, and why the whole world is now forced to pick a side. In 1987, a man named Ren Zhengfei started a small trading company in Shenzhen with almost nothing. He grew up poor, one of 7 kids in a family that didn't always have enough food. Before he built anything, he worked as a military engineer, learning how to solve problems with barely any resources. He didn't start his company because he had a big dream. He started it to feed his family. That company was Huawei. For years, Huawei stayed quiet. They built phone networks in places bigger companies ignored. Slowly, they moved into smartphones, and by 2019, they had become the second biggest phone maker on the planet, right behind Apple, selling in over 170 countries. Most people in the West had never even heard of them. Then the United States government called Huawei a national security threat. Washington cut them off from American chips and American software. Allies were pressured to do the same. A year later, the world's most important chip factory, TSMC in Taiwan, stopped supplying them completely. Overnight, a company that had just beaten Apple in phone sales could not get the parts to build a single phone. Picture a busy restaurant that suddenly can't buy a stove or a fridge, but the owner is still told to serve customers. That was Huawei in 2020. Suppliers who had worked with them for years cut ties in days. Most analysts thought this was the end. So Huawei started rebuilding from scratch. They redesigned thousands of circuit boards. They replaced over 13,000 band parts with things they designed themselves. They built their own operating system after losing Google's software. Every door that closed, they tried to build a new one. And remember that 0 number from the start of this story. This rebuild is exactly what made that 0 possible. Inside Huawei sits a chip design team called HiSilicon, founded back in 2004 when nobody thought it would matter much. After the sanctions hit, this small team became the center of Huawei's survival plan. Their biggest project was a line of AI chips called Ascend. Think of an AI chip like a car engine. The bigger and more efficient it is, the more work it can do at once, and in AI, that work means training massive systems that power chatbots and self-driving software. For years, NVIDIA built the best engines on the planet, and almost nobody came close. Huawei's answer was the Ascend 910C. By 2025, they were struggling to make enough of them fast enough. Bloomberg reported Huawei planned to roughly double production in 2026, aiming for around 600,000 of these chips, with total output across the whole Ascend line climbing as high as 1.6 million units. That's not a lab project anymore. That's a full assembly line running around the clock. But there was a massive wall in front of them. Designing a chip is one thing, manufacturing it is another. The most advanced chip factories use a machine called an EUV lithography system, so precise it can trace patterns smaller than a human hair. Only one company on Earth makes these machines, a Dutch company called ASML, and each one costs over $200 million. The United States blocked ASML from selling its newest machines to China. Without that tool, almost every expert assumed China simply could not build advanced chips. It would be like trying to build a skyscraper with only hand tools. China's biggest chip factory, SMIC, refused to accept that. Instead of the newest machines, their engineers used older equipment they were still allowed to buy, called deep ultraviolet lithography. They ran the same silicon wafer through the machine multiple times, using a technique called multiple patterning. Picture tracing over the same drawing several times with a slightly different stencil each pass, adding a little more detail each time. It sounds simple, but it's brutally hard. One tiny misalignment ruins the whole chip. It's slower, more expensive, and the yield is far lower than top factories get. Industry estimates put SMIC's yield somewhere between 15 and 40%, while the best factories in Taiwan and South Korea get well over 90%. That means over half the chips from some batches end up in the trash, in a normal market that would kill the whole plan. China didn't treat this like a normal market. By mid-2025, SMIC had used this method to produce working 5-nanometer chips for Huawei, without a single EUV machine involved. A former TSMC vice president told Bloomberg it was simply not possible for the United States to fully stop China from improving its chip technology. Push a country hard enough, he said, and they find a way. In April 2026, Huawei unveiled the Ascend 950 PR at an event in Shenzhen packed with executives from China's biggest tech companies. On paper, it delivers roughly 1.5 petaflops of processing power, meaning it can do 1 quadrillion calculations every second. And it carries over 100 gigabytes of high-speed memory. That puts it in the same conversation as some of NVIDIA's best hardware. That was enough for China's biggest companies. Alibaba and Tencent placed major orders. ByteDance alone committed over $5.5 billion to Huawei chips for its data centers. By some estimates, Huawei's Ascend line is on track to capture roughly 60% of the entire AI chip market inside China by the end of 2026, with revenue projected past $12 billion.
A team of engineers in China just made a small stack of chips beat a full-size graphics card by 149 times, and they did it using light instead of wires. This is not a rumor or a marketing claim. It is a peer-reviewed result out of Peking University, and it exposes a weakness in every AI chip built today. The story is not about China replacing NVIDIA. It is about something far more important hiding underneath that headline number. Every AI chip sold today is judged by one number: teraflops. That number tells you how fast a chip can do math under perfect conditions. It does not tell you how much time that chip spends doing nothing, just waiting for data to arrive. This waiting is called the memory wall, and researchers say it is the biggest hidden problem in modern computing. A graphics card can have thousands of cores ready to work, but if the data cannot reach those cores fast enough, most of that power sits idle. The team at Peking University decided to attack this waiting problem directly instead of building a bigger chip. They took a neural network with 5 layers and split it across 5 separate FPGA chips. An FPGA is a chip that can be rewired for one specific job instead of running general code like a normal processor. Each FPGA was permanently assigned one layer of the network. The first chip only ever handled layer 1, the second chip only ever handled layer 2, and so on through all 5 boards. Instead of connecting these chips with normal copper wires, the team connected them with light. Each FPGA got its own silicon photonic transceiver, a small device that turns electrical signals into pulses of light and back again. Each transceiver could move data at 400 gigabits per second. The light traveled using 4 different wavelengths at 1270, 1290, 1310, and 1330 nanometers, all packed onto the same fiber at once. These light signals pass through a 16x6 optical switch, a piece of hardware that can send light from any input to any output without slowing down or losing signal. Here is why light mattered so much. A normal network switch has to check, hold, and schedule every packet of data before sending it forward. That takes time. An optical switch skips almost all of that. It is closer to a clear path for light to travel straight through.